It's only the third interstellar visitor we've ever seen, but why does 3i Atlas behave like nothing else we've found drifting through our cosmic neighbourhood? I'm talking about an object that's currently racing through our solar system at speeds that would make your head spin, carrying with it secrets from a part of the galaxy we've never seen up close before. Now, you might have caught headlines about this mysterious visitor, but tonight we're going deeper than the usual surface-level coverage. We're going to uncover what scientists actually know about this enigmatic traveller, and perhaps more importantly, what still has them scratching their heads and staying up late running calculations that don't quite add up. Welcome back to The Weary Researcher. Tonight we're diving into something extraordinary, something that has astronomers around the world both excited and deeply puzzled. Before we embark on this journey together, I'd love to know where you're tuning in from and what time it is in your corner of our small blue planet. It brings me joy to see where all the fellow cosmic enthusiasts are from. If you find yourself drawn to these cosmic puzzles, these gentle explorations of the universe's deepest secrets, I'd be ever so grateful if you gave this video a like and perhaps subscribed. The story begins on a quiet summer morning. In the early hours of July 1st, 2025, a telescope in the Chilean desert captured something extraordinary. A faint dot moving against the star field, travelling at an impossible speed of 130,000 miles per hour. This wasn't just another asteroid or comet from our solar system. This was something from the depths of interstellar space, and it's already challenging everything we thought we knew about these mysterious cosmic wanderers. Most coverage of 3i Atlas has focused on the basic facts. It's fast, it's from another star system, and it's the third such object we've ever detected. But today, we're going deeper. We're going to explore the data that's keeping astronomers awake at night, the anomalies that don't fit any existing models, and the theories, both conventional and extraordinary, about what this object might actually be. Because after weeks of observation, one thing has become clear. 3i Atlas is not behaving like any interstellar object we've seen before. The story begins on July 1st, 2025, when the Atlas telescope, that's the Asteroid Terrestrial Impact Last Alert System, in Rio Hurtado, Chile, detected what initially appeared to be another near-Earth asteroid. The Atlas telescope is part of a NASA-funded network designed to scan the skies for potentially hazardous objects. But on this particular night, it found something far more exotic. The object was moving in a way that immediately caught the attention of astronomers around the world. Within hours of the discovery, telescopes across 3 continents were trained on this mysterious visitor. The Deep Random Survey Telescope in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope at Mauna Kea all began tracking its path. What they found was unprecedented. This wasn't just another space rock that had wandered too close to our solar system. This was an interstellar interloper, only the third ever confirmed in human history. The designation 3i Atlas tells us everything we need to know about its significance. The 3i stands for Third Interstellar, placing it in the exclusive company of Oumuamua, discovered in 2017, and Comet 2i Borisov, discovered in 2019. But from the moment astronomers began analysing its trajectory, it was clear that 3i Atlas, from here on, we'll simply call it Atlas, was going to rewrite the playbook on interstellar objects. Colin Orion Chandler, from the NSF DOE Vera C. Rubin Observatory, was among the first to publish detailed observations of the object. Working with data collected between June 21st and July 7th, including pre-discovery images that showed the object had been visible for weeks before anyone noticed it, Chandler's team determined that Atlas likely has a nucleus about 5.6 kilometers across, give or take 0.7 kilometers. That makes it roughly 3.5 miles wide, significantly larger than Oumuamua, but comparable in size to Comet Borisov. But size was just the beginning of the surprises. The object's brightness, measured at an absolute V-band magnitude of about 13.7 suggested something unusual about its composition or structure. Unlike most asteroids, which appear relatively dim and rocky, Atlas was reflecting light in patterns that suggested the presence of dust, lots of it. NASA's Transiting Exoplanet Survey satellite, or TESS, provided crucial pre-discovery coverage that allowed astronomers to track the object's behaviour over a longer time frame. These observations revealed something extraordinary. Atlas was not only moving faster than any interstellar object previously recorded, but it was following a trajectory that brought it surprisingly close to the plane of our solar system, what astronomers call the ecliptic. Most interstellar objects arrive at steep angles to the ecliptic, diving down from above or below the plane of the planets like cosmic javelins. But Atlas is different. Its orbital inclination is less than 5 degrees from the ecliptic plane, meaning it's travelling almost parallel to the orbits of Earth, Mars and Jupiter. This is statistically unlikely for a random interstellar wanderer, and it immediately raised questions about the object's origins. The trajectory analysis revealed another crucial piece of information. Atlas is following what's called a hyperbolic orbit. Unlike elliptical orbits that keep objects bound to the Sun, hyperbolic orbits are open-ended, meaning the object has more than enough velocity to escape our solar system's gravitational pull. The eccentricity of its orbit, a measure of how elongated the path is, confirmed what astronomers had suspected from the beginning. This object came from interstellar space and will return to interstellar space, making only a brief pass through our cosmic neighbourhood. But here's where things start to get strange. When astronomers compared Atlas to its two predecessors, the differences were immediately apparent. Oumuamua had been a puzzle from the start, an elongated, tumbling object that showed no signs of cometary activity despite receiving a small, unexplained acceleration as it moved away from the Sun. Comet 2I Borisov, on the other hand, behaved exactly like comets from our own solar system, developing a bright coma and tail as solar radiation sublimated ice from its surface. Atlas seemed to fall somewhere in between, and that's where the real mystery begins. Early spectroscopic observations of Atlas revealed something puzzling. Instead of the clear spectral signatures of sublimating gases that characterize active comets, astronomers detected primarily dust and reddening of the light, a sign that the object was surrounded by fine particles rather than the typical mix of gas and dust seen in cometary comas. This was particularly strange given that the object was clearly active, displaying what appeared to be a faint coma and possibly even a tail in some images. The absence of clear gas signatures in the early spectroscopic data led to intense debate among astronomers. Dr. Alan Hale, co-discoverer of comet Hale-Bopp, was among those who initially reported no clear cometary features. But as more observations poured in from telescopes around the world, a more complex picture began to emerge. On July 2nd, just one day after the official discovery, multiple observatories began detecting marginal but definite signs of cometary activity. The Deep Random Survey Telescope in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope all captured images showing a faint coma, the fuzzy atmosphere of gas and dust that surrounds an active comet nucleus, along with what appeared to be the beginnings of a tail-like structure. This was when NASA's Hubble Space Telescope entered the picture. Hubble's exquisite resolution and sensitivity allowed astronomers to see details that ground-based telescopes had missed. The Space Telescope revealed what mission scientists described as a teardrop-shaped cocoon of dust surrounding the object's nucleus. This wasn't the typical symmetrical coma of a normal comet, but rather an asymmetric structure that suggested complex processes were at work on the object's surface. The Hubble observations were particularly revealing because they showed the object's motion against the background stars. As Atlas raced along its hyperbolic trajectory, the stationary stars appeared as streaks in the long exposure images, while the comet itself remained sharp and focused. This technique allowed astronomers to measure the object's position with unprecedented accuracy and refine their calculations of its orbit and origin. But perhaps the most significant breakthrough came from an unexpected source. NASA's Neil Gehrels Swift Observatory, a space telescope designed to study gamma-ray bursts and other high-energy phenomena, turned its ultraviolet cameras toward Atlas. What it found would change our understanding of this mysterious visitor forever. Swift detected the unmistakable signature of water vapor surrounding Atlas, the first confirmed detection of water activity in the object. This wasn't just the sublimation of surface ice, but active outgassing that indicated the presence of subsurface volatiles being heated and released as the comet approached the Sun. The detection of water was significant not just because it confirmed the object's cometary nature, but because it provided the first chemical fingerprint of material from another solar system. The water detection also helped explain some of the earlier puzzles. The reason early spectroscopic observations had missed the gas signatures wasn't because they weren't there, but because they were subtle and required the specialized capabilities of space-based ultraviolet telescopes to detect. Ground-based telescopes, hampered by atmospheric absorption and the object's distance from Earth, simply couldn't see the full picture. However, even with the water detection, mysteries remained. Follow-up observations expected to detect other common cometary volatiles like carbon dioxide and carbon monoxide have so far come up empty. This is unusual, as most comets from our own solar system show a rich mix of different ices sublimating at various distances from the Sun. The apparently selective outgassing of Atlas raised new questions about its composition and thermal history. The object's rotation also presented puzzles. While astronomers were able to determine that Atlas rotates with a period of several hours, the exact rotation rate and the orientation of its spin axis proved difficult to pin down. This wasn't entirely surprising. Interstellar objects are notoriously challenging to study because of their speed and the limited time they spend in the inner solar system, where detailed observations are possible. But here's where the story takes a turn toward the truly extraordinary. Dr. Avi Loeb, the controversial Harvard astrophysicist who previously suggested that Oumuamua might be of artificial origin, began examining the data on Atlas with his characteristic combination of scientific rigor and willingness to consider unconventional possibilities. In a paper co-authored with Adam Hibbard and Adam Krull from the Initiative for Interstellar Studies in London, Loeb highlighted what he called various anomalous characteristics displayed by Atlas during its early passage through our solar system. These anomalies, determined from photometric and astrometric observations, didn't fit neatly into existing models of natural cometary behavior. Loeb's analysis focused on several key observations. First, there was the unusual dust-to-gas ratio observed in early spectroscopic studies. While later observations would detect water vapor, the initial predominance of dust over gas was atypical for a comet at Atlas's distance from the Sun. Second, there was the object's trajectory, not just its near-ecliptic orbit, but subtle variations in its path that suggested complex outgassing patterns, or possibly even structural changes within the object itself. Most intriguingly, Loeb pointed to the object's apparent resistance to some of the non-gravitational forces that typically affect comets. When comets approach the Sun, the sublimation of ice from their surfaces creates jets of gas and dust that can slightly alter their trajectories, a phenomenon known as the rocket effect. But Atlas seemed to be experiencing these forces in unexpected ways, leading to what Loeb described as anomalous photometric and astrometric behavior. The Harvard physicist was careful to present these observations within a framework of scientific hypothesis testing. The simplest explanation, he acknowledged, was that Atlas is indeed a comet, and that early observations had simply missed some of the gas signatures due to the object's distance from Earth and the limitations of ground-based spectroscopy. This interpretation gained support as more sophisticated observations revealed water vapour and the characteristic teardrop-shaped dust coma. But Loeb also raised a more provocative possibility. What if future observations continued to show anomalous behaviour that couldn't be explained by conventional cometary physics? What if the object's dust production, trajectory variations, or other characteristics suggested something more exotic than a simple, dirty snowball from another star system? This line of thinking wasn't entirely unprecedented. Oumuamua had displayed its own set of anomalies, most notably a small but measurable acceleration as it moved away from the Sun, an acceleration that occurred without any detected outgassing or other obvious cause. While most astronomers eventually settled on explanations involving hidden outgassing of hydrogen or other exotic processes, the Oumuamua case had opened the door to more speculative possibilities about the nature of interstellar visitors. The scientific community's reaction to Loeb's Atlas hypothesis was swift and largely skeptical. Dr. Jason Wright, an astronomer at Penn State University who has studied both natural and potentially artificial phenomena in space, described Loeb's approach as premature and based on incomplete data. Writing on his blog, AstroWrite, Wright noted that by July 12th, just 11 days after the discovery, Loeb had already begun suggesting that Atlas might be artificial based on limited spectroscopic data that showed dust reddening but no clear gas signatures. Wright pointed out that early observations of any comet are typically dominated by dust, especially when the object is still relatively far from the Sun, and observations are challenging due to the object's faintness and rapid motion. The absence of easily detectable gas signatures in the first few days or weeks of observations didn't necessarily indicate anything anomalous. It was simply a reflection of the limitations of early observational data. Other astronomers echoed Wright's concerns. Dr. Michelle Bannister, a planetary astronomer who specializes in small bodies from the outer solar system, noted that interstellar objects present unique observational challenges that can easily lead to misinterpretation of early data. The combination of high velocities, large distances, and limited observing windows means that astronomers often have to make do with fragmentary information, at least in the early stages of an object's discovery. The controversy over Atlas's nature reflects a broader tension within the astronomical community about how to approach the study of interstellar visitors. On one hand, these objects represent unprecedented opportunities to study material from other star systems, a scientific treasure trove that demands careful, thorough investigation. On the other hand, their rarity and the limited time available for observations create pressure to draw conclusions quickly, sometimes based on incomplete data. This tension becomes even more pronounced when public interest and media attention focus on the more sensational possibilities. The idea that Atlas might be artificial, a probe from another civilization, generates headlines and captures imaginations in ways that conventional cometary science simply cannot match. But the scientific process requires patience, skepticism, and the accumulation of evidence over time, qualities that don't always align with the 24-hour news cycle. Despite the controversies, the scientific study of Atlas continued at a furious pace. Observatories around the world coordinated their efforts to maximize the scientific return from this rare opportunity. The European Southern Observatory's Very Large Telescope in Chile began long-term monitoring of the object's brightness and spectral characteristics. The Gemini Observatory, with telescopes in both Chile and Hawaii, initiated a comprehensive study of the comet's coma and potential tail development. One of the most significant developments came from analysis of the object's trajectory and origin. By working backwards along Atlas's path through space, astronomers attempted to determine which star system it might have originated from. This type of analysis is notoriously difficult because stellar motions change over the millions of years it takes for objects to travel between star systems, and because small uncertainties in measured velocities can lead to large errors when extrapolated over such vast distances and timescales. Initial calculations suggested that Atlas had been travelling through interstellar space for millions of years, possibly originating from the direction of the constellation Sagittarius. This region of the sky is particularly rich in stars because it's the direction toward the centre of our galaxy, making it statistically likely that any random interstellar object might appear to come from that general area. However, more detailed analysis revealed something unexpected. Unlike most interstellar objects, which should arrive at our solar system from essentially random directions, Atlas appeared to be following a trajectory that brought it remarkably close to the ecliptic plane. The probability of this happening by chance was low, leading some astronomers to speculate about whether the object's path might have been influenced by gravitational encounters with other stars or planetary systems during its long journey through space. The near-ecliptic trajectory had another important implication. It meant that Atlas would remain visible to Earth-based telescopes for a longer period than objects arriving at steep angles to the solar system. This extended observability was a tremendous advantage for astronomers, providing more opportunities to study the object's behaviour and characteristics in detail. As observations continued, the picture of Atlas became both clearer and more complex. The Swift Observatory's detection of water vapour was confirmed and refined by additional ultraviolet observations. The Hubble Space Telescope provided increasingly detailed images of the object's coma structure, revealing subtle changes in the dust distribution as Atlas responded to increasing solar heating. Ground-based telescopes contributed their own pieces to the puzzle. The Palomar Observatory's 200-inch telescope captured high-resolution images showing the development of what appeared to be a short, stubby tail. Not the elegant, flowing tail of a typical comet, but a more modest structure that suggested relatively weak outgassing activity. Spectroscopic observations became more sophisticated as well. While early spectra had shown primarily dust reddening, more sensitive instruments began to detect subtle absorption lines that hinted at the presence of various molecular species in the coma. Water was the strongest signal, but there were also tentative detections of hydroxyl radicals, the breakdown products of water molecules dissociated by solar ultraviolet radiation. The absence of carbon dioxide and carbon monoxide in the spectra remained puzzling, however. These molecules are common in comets from our own solar system and are typically among the first volatiles to sublimate as a comet approaches the Sun. Their apparent absence in Atlas suggested either that the object had a very different composition from solar system comets, or that its thermal history had somehow depleted these particular volatiles. One possibility was that Atlas had originated in a very different type of stellar system than our own. Stars with different masses, ages, and metallicities create planetary systems with different compositions, and the comets formed in such systems might indeed have very different ice compositions than those we're familiar with. This interpretation was exciting because it suggested that Atlas might provide our first detailed look at the chemistry of planet formation around another star. Another possibility was that the object had undergone thermal processing during its long journey through interstellar space. While the space between stars is incredibly cold, just a few degrees above absolute zero, cosmic rays and other forms of radiation can slowly alter the chemical composition of small objects over millions of years. Perhaps Atlas had lost its more volatile components during its interstellar wanderings, leaving behind a composition dominated by water ice and dust. The debate over Atlas's nature was further complicated by the object's apparent resistance to detailed characterization. Unlike Comet 2I Borisov, which had behaved predictably and allowed astronomers to determine its composition rotation period, and other properties with reasonable confidence, Atlas remained stubbornly enigmatic. Its brightness varied in ways that didn't fit simple models of cometary outgassing, and its spectral characteristics seemed to change from observation to observation in subtle but significant ways. Part of the challenge was simply the object's speed. At 130,000 miles per hour, Atlas was moving faster than any previously studied interstellar object, making it difficult to accumulate the long exposure times needed for detailed spectroscopy. The object was also relatively faint, requiring large telescopes and excellent observing conditions to study effectively. But beyond these technical challenges, there seemed to be something fundamentally different about Atlas that made it resistant to easy categorization. It wasn't quite like Oumuamua, which had appeared almost completely inert until its mysterious acceleration was detected. It wasn't quite like 2I Borisov, which had behaved like a textbook comet from beginning to end. Instead, Atlas seemed to occupy a middle ground, showing clear signs of activity, but in ways that didn't match any existing templates. This ambiguity became the focus of intense scientific debate. Conservative astronomers argued that the apparent anomalies were simply the result of observational limitations and incomplete data. Given more time and better observations, they contended Atlas would reveal itself to be a perfectly normal, if perhaps unusually large and fast, interstellar comet. More speculative researchers suggested that the anomalies might be real and could indicate something genuinely new about the nature of interstellar objects. Perhaps comets from other stellar systems really were fundamentally different from those in our own solar system. Perhaps the interstellar environment altered objects in ways that weren't yet fully understood. Or perhaps, and this was the most controversial possibility, some interstellar visitors weren't natural objects at all. The artificial origin hypothesis championed by Avi Loeb and his colleagues was based on more than just the early spectroscopic anomalies. They pointed to the object's unusual trajectory, its apparently selective outgassing, and its resistance to straightforward characterization as potential signs of artificial construction. While they were careful to present this as just one hypothesis among many, the implications were profound. If Atlas were indeed artificial, a probe from another civilization, it would represent the most significant discovery in human history. It would mean that we were not alone in the universe, and that at least one other technological civilization had achieved the ability to send objects across interstellar space. The probe hypothesis also raised unsettling questions about the intentions of its creators and whether additional artificial objects might be visiting our solar system undetected. The scientific mainstream remained deeply skeptical of the artificial origin hypothesis, however. Dr. Robert Werrick, one of the discoverers of Oumuamua, pointed out that extraordinary claims require extraordinary evidence, and that the anomalies observed in Atlas fell well within the range of natural phenomena that might be expected from an object of unknown composition and thermal history. Other researchers noted that the history of astronomy was filled with apparent anomalies that were later explained by conventional physics once better observations became available. The canals of Mars, the steady-state universe, and countless other mysteries had eventually yielded to more mundane explanations as observational techniques improved and theoretical understanding advanced. The debate over Atlas's nature was also complicated by the broader context of the search for extraterrestrial intelligence. Programs like SETI had been scanning the skies for decades, looking for signals from alien civilizations, so far without success. The possibility that evidence of extraterrestrial technology might arrive in the form of a physical object rather than a radio signal was intriguing, but it also seemed statistically unlikely. If alien civilizations were sending probes to nearby star systems, basic calculations suggested that we should be seeing many more such objects than just one every few years. The fact that Oumuamua, 2I Borisov, and Atlas were separated by years rather than months or weeks suggested that interstellar visitors were relatively rare, more consistent with natural objects ejected from other planetary systems than with a systematic exploration program by advanced aliens. However, proponents of the artificial hypothesis countered that our sample size was still far too small to draw definitive statistical conclusions. With only 3 confirmed interstellar visitors, it was impossible to say whether the current detection rate represented the true frequency of such objects, or was simply limited by our observational capabilities. Surveys like ATLAS were relatively new and might be detecting only the largest and most active interstellar objects, missing smaller or more passive visitors entirely. The uncertainty was compounded by the fact that determining whether an object is of interstellar origin requires careful orbital analysis, which can take weeks or months after initial detection. It was entirely possible that other interstellar objects had passed through the solar system unrecognized, classified as ordinary asteroids or comets before their true nature could be determined. As ATLAS continued its journey through the solar system, astronomers raced to gather as much data as possible before the object faded from view. The comet had passed its closest approach to the Sun in late July 2025 and was now heading back toward interstellar space. Each passing day made observations more challenging as the object grew fainter and more distant. The Vera C. Rubin Observatory, currently under construction in Chile, represented the next generation of survey telescopes that might revolutionize the study of interstellar visitors. Once operational, Rubin would scan the entire visible sky every few nights, potentially detecting dozens or even hundreds of interstellar objects per year. This flood of new discoveries would provide the statistical sample needed to determine whether objects, like ATLAS, were truly anomalous or simply represented the natural diversity of interstellar wanderers. In the meantime, astronomers were making the most of every available photon from ATLAS. The European Space Agency's Gaia spacecraft, primarily designed to map the positions and motions of stars, turned its exquisitely sensitive instruments toward the interstellar visitor. Gaia's measurements could potentially detect minute changes in the object's trajectory that might reveal additional information about its internal structure or composition. NASA's James Webb Space Telescope, the most powerful infrared observatory ever built, also joined the effort. Webb's infrared capabilities were particularly valuable for studying the thermal properties of ATLAS and detecting molecular species that might be invisible to optical telescopes. The Space Telescope's observations could potentially resolve the mystery of the missing carbon compounds and provide a more complete picture of the object's chemical composition. Ground-based radar systems also attempted to study ATLAS, though the object's distance and speed made such observations extremely challenging. The Arecibo Observatory in Puerto Rico had been lost to structural collapse in 2020, eliminating one of the most powerful planetary radar systems. The remaining facilities at Goldstone in California and Greenbank in West Virginia pushed their capabilities to the limit in attempts to detect radar echoes from the rapidly receding object. Each new observation added pieces to the puzzle, but the overall picture remained frustratingly incomplete. Some measurements supported the conventional comet hypothesis, while others seemed to hint at more exotic possibilities. The water detections clearly established that ATLAS contained ice and was responding to solar heating in ways consistent with cometary behavior. But the unusual dust-to-gas ratios, the selective outgassing, and the object's resistance to detailed characterization continued to fuel speculation about its true nature. The public fascination with ATLAS grew as news of the various theories spread through social media and popular science outlets. The possibility that humanity might be witnessing its first confirmed encounter with alien technology captured imaginations around the world, despite the scientific community's emphasis on the need for more data and careful analysis. Amateur astronomers also joined the effort to study Atlas, using sophisticated CCD cameras and computerized telescopes to track the object's brightness and position. While their equipment couldn't match the sensitivity of professional observatories, the distributed network of amateur observers provided valuable long-term monitoring that complemented the snapshot observations from larger facilities. The citizen science aspect of Atlas research highlighted one of the most remarkable aspects of modern astronomy: the democratization of space exploration. Advanced technology had made it possible for dedicated amateurs to contribute meaningful data to cutting-edge research, expanding the global community of researchers working to understand this mysterious visitor. Educational institutions around the world also incorporated Atlas into their curricula, using the object as a real-time case study in astronomical research methods and scientific hypothesis testing. Students followed the daily developments in observations and analysis, learning firsthand how science operates when faced with genuinely new and puzzling phenomena. The interdisciplinary nature of Atlas research also became apparent as the investigation progressed. Astronomers collaborated with planetary scientists to understand the object's thermal behavior, with chemists to interpret spectroscopic data, and with physicists to model the complex interactions between solar radiation and the object's surface materials. The study of a single small object required expertise from across the scientific spectrum. International cooperation was essential as well. Atlas's rapid motion meant that observations had to be coordinated across multiple time zones and continents to maintain continuous coverage. Telescopes in Chile observed during their nighttime hours, then handed off to facilities in Hawaii and California as Earth's rotation carried the object into their fields of view. European observatories contributed during their optimal viewing windows, creating a global network of instruments focused on this single, fleeting target. The logistical challenges of coordinating such observations were immense. Telescope time is precious and typically allocated months or years in advance, but the appearance of Atlas required immediate, flexible scheduling. Observatory directors had to balance the scientific importance of studying this rare visitor against the needs of other research programs that had been planned long in advance. The financial costs were substantial as well. Operating major telescopes requires significant resources, from electrical power to specialized technical staff. The extended campaign to study Atlas represented a major investment by the international astronomical community, justified by the object's unique scientific value, but nonetheless requiring difficult decisions about resource allocation. Despite these challenges, the scientific return from Atlas observations was already proving substantial, even if the object turned out to be a relatively conventional interstellar comet. The detailed study of its composition and behavior was providing unprecedented insights into the chemistry and physics of planet formation around other stars. The water detections, for example, confirmed that the processes that create icy planetesimals in our own solar system also operate around other stars. This was important for understanding the potential for life elsewhere in the galaxy, since water is considered essential for life as we know it. The presence of water ice in an object from another stellar system suggested that the ingredients for life might be common throughout the galaxy. The unusual composition of Atlas, particularly the apparent absence of carbon dioxide and carbon monoxide, also provided clues about the diversity of planetary systems. If these differences were real and not simply observational artifacts, they suggested that stellar systems with different properties might produce very different types of small bodies. This diversity could have important implications for understanding how planetary systems evolve and what conditions might be necessary for the development of life. The trajectory analysis of Atlas was contributing to our understanding of the dynamics of interstellar space as well. The object's path through the galaxy could potentially be traced back to its stellar system of origin, providing information about the gravitational environment it had experienced during its long journey. Such information was valuable for understanding how objects move between star systems and how frequently such transfers might occur. The study of Atlas was also advancing observational astronomy more generally. The techniques developed to characterize rapidly moving, faint objects were applicable to many other areas of research. The coordination methods used to organize global observing campaigns could be applied to future transient events. The data analysis methods used to extract meaningful information from limited datasets would benefit the study of other challenging astronomical objects. But perhaps the most important contribution of Atlas was its role in expanding human perspectives on our place in the cosmos. Regardless of whether the object turned out to be a conventional comet or something more exotic, its very existence reminded us that our solar system is not isolated from the broader galaxy. We are part of a vast, dynamic universe in which material, and perhaps information, flows between star systems on timescales of millions of years. The philosophical implications of Atlas were profound. If the object were indeed artificial, it would mean that intelligence had achieved the ability to reach across the interstellar void, expanding the scope of civilizations beyond single planetary systems. Even if it were natural, it represented a tangible connection to other worlds, carrying within its ices and minerals the story of planet formation under alien suns. The public response to Atlas also revealed something important about human nature and our relationship with the unknown. The widespread fascination with the possibility of alien technology reflected a deep-seated desire to know that we are not alone in the universe. The careful, methodical approach of the scientific community, in contrast, demonstrated our species' hard-won ability to distinguish between what we hope to be true and what the evidence actually supports. This tension between wonder and skepticism is at the heart of scientific progress. The sense of wonder drives us to ask questions and seek answers, while skepticism ensures that our answers are reliable and based on evidence rather than wishful thinking. Atlas embodied this duality perfectly. It was genuinely mysterious and deserving of careful study, but it also demanded rigorous analysis rather than speculative leaps. As the weeks passed and Atlas continued its outbound journey, the initial excitement began to settle into the more routine work of scientific analysis. Data from dozens of telescopes had to be calibrated, cross-checked, and synthesized into a coherent picture of the object's properties. Spectroscopic observations required careful modeling to separate the signatures of different molecular species. Photometric data had to be analyzed to understand the object's rotation, shape, and surface properties. The process was painstaking and often tedious, far removed from the dramatic headlines that had accompanied the initial discovery. But this was where the real science happened. Not in the moment of discovery, but in the months and years of careful analysis that followed. Only through this methodical process could astronomers hope to distinguish between genuine anomalies and observational artifacts, between revolutionary discoveries and conventional phenomena seen from new angles. The preliminary results from this analysis were tantalizing but incomplete. The water detections had been confirmed and refined, providing clear evidence of cometary activity. The unusual dust properties had been partially explained by models of dust grain formation under different chemical conditions than those found in our solar system. The object's trajectory had been precisely determined, ruling out some of the more exotic orbital scenarios that had been proposed early in the observation campaign. But mysteries remained. The selective outgassing that had initially puzzled astronomers was still not fully explained. The object's brightness variations continued to show patterns that didn't match simple models of rotating, outgassing nuclei. And the fundamental question of Atlas's origin, which star system it came from, and how it acquired its unusual trajectory, remained unanswered. The ongoing analysis was also revealing the limitations of current astronomical techniques. Despite the unprecedented international effort to study Atlas, many basic questions about the object remained difficult to answer. Its exact size, shape, rotation period, and internal structure were all still uncertain. The composition of its nucleus could only be inferred indirectly from observations of its coma and spectroscopic signatures. These limitations highlighted the need for new approaches to studying interstellar visitors. Future missions might include dedicated space telescopes optimized for detecting and characterizing fast-moving objects. Spacecraft missions to intercept interstellar visitors were also being discussed, though the technical challenges would be immense given the velocities involved. The European Space Agency had already begun studying the feasibility of an interstellar probe mission that could be launched toward the next detected interstellar visitor. Such a mission would require revolutionary propulsion technology and unprecedented precision in trajectory planning, but it could provide close-up images and direct chemical analysis that would be impossible from Earth-based observations. NASA's Jet Propulsion Laboratory was also investigating concepts for rapid response missions that could be launched within months of detecting a new interstellar object. These Comet interceptor spacecraft would need to be pre-built and waiting in storage, ready for launch as soon as a suitable target was identified. The technical challenges were formidable, but the scientific rewards would be extraordinary. The study of Atlas was also driving advances in artificial intelligence and machine learning applications to astronomy. The volume of data generated by modern surveys was already overwhelming traditional analysis methods, and objects like Atlas that required rapid characterization were pushing astronomers to develop automated systems capable of real-time analysis and decision-making. Machine learning algorithms were being trained to recognize the spectroscopic signatures of different types of interstellar objects, potentially allowing future discoveries to be classified and prioritized within hours rather than weeks. Computer vision systems were being developed to automatically detect and track fast-moving objects in survey images, reducing the reliance on human observers who might miss faint or rapidly moving targets. The Atlas campaign was also revealing the importance of international coordination in modern astronomy. No single nation or institution had all the resources necessary to fully characterize an interstellar visitor. Success required unprecedented cooperation between observatories, space agencies, and research institutions around the world. This cooperation was not without its challenges. Different countries had different priorities, funding mechanisms, and decision-making processes. Language barriers and time zone differences complicated communication. Political tensions occasionally threatened to interfere with scientific collaboration. But the shared fascination with Atlas generally overcame these obstacles, demonstrating the unifying power of scientific curiosity. The media coverage of Atlas also highlighted the challenges of communicating complex scientific concepts to the general public. Early reports had focused on the most sensational possibilities, alien probes and mysterious anomalies, often neglecting the more mundane but equally important scientific work of characterizing the object's basic properties. Scientists involved in the research found themselves walking a delicate line between honest acknowledgement of uncertainties and responsible communication of what the data actually showed. The public appetite for definitive answers often clashed with the scientific reality that understanding develops gradually through the accumulation of evidence over time. Social media amplified both the benefits and the challenges of public engagement with the Atlas research. On the positive side, platforms like Twitter and YouTube allowed scientists to communicate directly with interested members of the public, sharing updates and insights in real time. Amateur astronomers could share their own observations and contribute to the global understanding of the object. But social media also facilitated the spread of misinformation and wild speculation. Conspiracy theories about government cover-ups and alien visitation proliferated alongside legitimate scientific discussion. The challenge for scientists was to maintain public engagement while combating misinformation and maintaining appropriate scientific skepticism. The Atlas case also raised important questions about scientific priorities and resource allocation. The intensive effort to study this single object had required diverting telescope time and resources from other important research projects. While the scientific value of studying interstellar visitors was unquestionable, the astronomical community had to grapple with the opportunity costs of such focused campaigns. Some researchers argued that the resources devoted to Atlas could have been better spent on systematic surveys aimed at finding more interstellar objects, rather than intensive study of a single visitor. Others contended that the detailed characterization of individual objects was essential for understanding the broader population, and that each interstellar visitor provided unique scientific opportunities that might not be repeated for years or decades. The debate reflected broader tensions within astronomy, between survey science and targeted observations, between breadth and depth in research strategies. There were no easy answers, but the Atlas experience was informing future planning for how the astronomical community might respond to similar discoveries. As autumn approached and Atlas continued its outbound journey, the object was becoming increasingly difficult to observe. Its distance from Earth was growing rapidly, and its brightness was fading as it moved farther from the Sun. Soon, it would be beyond the reach of even the largest telescopes, carrying its secrets back into the interstellar void. The final observations were precious, representing the last opportunities to gather data about this mysterious visitor. Astronomers pushed their instruments to the limit, extracting every possible photon from the fading object. Long exposure images captured the last wisps of its coma, while sensitive spectrographs strained to detect the faintest molecular signatures. By September 2025, Atlas had faded below the detection threshold of most telescopes. Only the largest instruments in the world could still track its motion against the background stars, and even they were nearing their limits. The intensive observation campaign that had consumed the astronomical community for months was drawing to a close. The end of observations marked the beginning of a new phase in the Atlas story. With no new data coming in, astronomers could finally step back and synthesize everything they had learned. The months of frantic observing would be followed by years of careful analysis, modelling, and theoretical work aimed at understanding what this object represented. The preliminary consensus was that Atlas was most likely a large interstellar comet with an unusual composition and thermal history. The water detections and cometary activity were consistent with this interpretation, and most of the apparent anomalies could be explained by the object's exotic origins and the challenging nature of the observations. But significant uncertainties remained. The selective outgassing patterns, the unusual dust properties, and the object's resistance to detailed characterization had not been fully explained. Some researchers continued to argue that Atlas might represent something genuinely new, either a type of natural object not previously encountered, or possibly something more exotic still. The debate over Atlas's nature was likely to continue for years as astronomers worked to extract every possible insight from the available data. Computer models would be refined, new theoretical frameworks would be developed, and the observations would be reanalyzed from new perspectives. Each iteration might reveal new details or clarify existing puzzles. The legacy of Atlas extended far beyond the specific question of what it was. The object had served as a catalyst for advances in observational techniques, international cooperation, and public engagement with science. It had pushed the boundaries of what was possible in rapid response astronomy and had highlighted both the capabilities and limitations of current astronomical infrastructure. Perhaps most importantly, Atlas had demonstrated that our solar system was not isolated from the broader galaxy. The object represented a tangible connection to other worlds, other stellar systems, and possibly other forms of matter organization that we had never encountered before. Even if it turned out to be a conventional comet, it carried within its structure the history of planet formation under alien conditions. The philosophical implications were profound. Atlas reminded us that we live in a dynamic universe where matter, energy, and perhaps information flow between star systems on vast timescales. The object that had briefly visited our cosmic neighborhood carried with it the potential to transform our understanding of our place in the galaxy. The search for additional interstellar visitors had intensified following the Atlas discovery. New survey programs were being planned, existing surveys were being expanded, and detection algorithms were being refined based on lessons learned from tracking this object. The astronomical community was preparing for the possibility that interstellar visitors might be more common than previously thought. The Vera C. Rubin Observatory, scheduled to begin operations in 2025, promised to revolutionize the detection of interstellar objects. Its wide field of view and sensitive cameras would survey the entire visible sky every few nights, potentially discovering dozens or hundreds of interstellar visitors per year. This flood of new discoveries would provide the statistical sample needed to understand whether Atlas was typical or exceptional. Future space missions were also being planned with interstellar visitors in mind. The European Space Agency's proposed Comet Interceptor mission could potentially be retargeted toward newly discovered interstellar objects. NASA was studying concepts for rapid response spacecraft that could be launched within months of detecting suitable targets. Ground-based telescopes were being upgraded with new instruments optimized for studying fast-moving objects. Adaptive optics systems were being improved to provide sharper images of distant, faint targets. Spectrographs were being redesigned to capture meaningful data from objects with limited observing windows. The Atlas experience had also highlighted the importance of pre-discovery observations in understanding interstellar visitors. The object had been visible in survey images for weeks before its interstellar nature was recognized, and these early observations had proven crucial for determining its orbit and properties. Automated systems were being developed to search through archival survey data for missed interstellar objects, potentially doubling or tripling the known sample. International cooperation was being formalized through new agreements and protocols for sharing data and coordinating observations. The informal networks that had emerged during the Atlas campaign were being institutionalized to ensure rapid response to future discoveries. Communication channels were being established to facilitate real-time coordination between observatories worldwide. The public engagement aspect of Atlas research was also evolving. Scientists had learned valuable lessons about communicating uncertainty and the scientific process to non-expert audiences. Educational materials were being developed to help the public understand how astronomical research works and why careful analysis takes time. Citizen science programs were being expanded to include amateur astronomers in the search for and study of interstellar visitors. Sophisticated analysis tools were being made available to non-professional researchers, democratizing access to cutting-edge astronomical research. The global community of interested observers was being organized into a network capable of contributing meaningfully to future discoveries. The economic implications of Atlas research were also becoming apparent. The intensive observation campaign had demonstrated the value of investing in astronomical infrastructure and international cooperation. The technological advances driven by the need to study fast-moving, faint objects had applications beyond astronomy, potentially benefiting other fields that required sensitive detection and rapid analysis. The Atlas discovery had also stimulated public interest in space science and astronomy, potentially inspiring a new generation of researchers and increasing support for scientific education and research funding. The object's mysterious nature had captured imaginations in ways that more routine astronomical discoveries could not match. As 2025 drew to a close, Atlas was well on its way back to interstellar space, but its impact on astronomy and human understanding continued to grow. Papers analysing various aspects of the observations were appearing in scientific journals, each adding new pieces to the puzzle of what this object represented. Some studies focused on the object's composition, using sophisticated models to interpret the spectroscopic data and understand how the observed molecules and dust grains might have formed. Others analysed the trajectory data, attempting to trace Atlas back to its stellar system of origin and understand the gravitational influences it had experienced during its journey. Theoretical papers explored the implications of Atlas for our understanding of planetary system formation and evolution. If interstellar objects like Atlas were common, they might play an important role in transferring material between stellar systems, potentially even spreading the chemical ingredients for life throughout the galaxy. The possibility that Atlas might be artificial continued to generate discussion, though the scientific mainstream remained skeptical. Avi Loeb and his colleagues published detailed analyses of the object's anomalous properties, while other researchers published rebuttals arguing that all the observed phenomena could be explained by natural processes. The debate was healthy and reflected the normal functioning of the scientific process. Extraordinary claims were being subjected to rigorous scrutiny, with researchers on all sides working to ensure that conclusions were based on solid evidence rather than wishful thinking or preconceived notions. Public opinion remained divided, with polls showing that a significant fraction of people believed Atlas might be of artificial origin, despite the lack of definitive evidence. This disconnect between public perception and scientific consensus highlighted ongoing challenges in science communication and the need for better educational programs about how science works. The Atlas story was also being incorporated into popular culture, appearing in science fiction novels, documentaries, and educational programs. The object had become a symbol of the mystery and wonder of the cosmos, representing humanity's ongoing quest to understand our place in the universe. As the first anniversary of the discovery approached in July 2026, astronomers began preparing retrospective analyses of everything they had learned from Atlas. The object would remain visible to the very largest telescopes for a few more months, but the intensive observation campaign was over. The focus was shifting from data collection to data analysis and interpretation. The preliminary results were intriguing but not revolutionary. Atlas appeared to be a large interstellar comet with some unusual properties, but most of its characteristics could be explained by conventional physics and chemistry. The early spectroscopic anomalies had been resolved by better observations, and the object's trajectory and behaviour were consistent with a natural origin. But mysteries remained. The object's exact composition was still uncertain, its internal structure was unknown, and its ultimate origin remained a matter of speculation. Some of the more subtle observational anomalies had not been fully explained, leaving room for continued debate and investigation. The scientific legacy of Atlas was already secure, regardless of what future analysis might reveal about its nature. The object had advanced our understanding of interstellar visitors, driven technological and methodological improvements in astronomy, and demonstrated the power of international scientific cooperation. More fundamentally, Atlas had reminded us that we live in a connected universe. The boundaries of our solar system are permeable, and material from other worlds regularly visits our cosmic neighbourhood. Whether natural or artificial, these visitors carry with them the potential to transform our understanding of the cosmos and our place within it. The search for the next interstellar visitor was already underway. Automated survey systems scanned the skies nightly, searching for the telltale motion that would signal another visitor from the stars. Machine learning algorithms trained on Atlas data were being deployed to flag potential candidates for human review. When the next interstellar object was discovered, and astronomers were confident that it was a matter of when, not if, the response would be faster and more coordinated than ever before. The Atlas experience had taught valuable lessons about how to organise rapid response observation campaigns and extract maximum scientific value from brief encounters with these cosmic messengers. The question that remained was what the next visitor would teach us. Would it be another mysterious object like Atlas, challenging our understanding and sparking new debates? Would it be a more conventional comet or asteroid that provided clear insights into the processes of planet formation around other stars? Or might it be something even more extraordinary, perhaps the definitive evidence of alien technology that some researchers believed Atlas might represent? Only time would tell, but one thing was certain: each interstellar visitor brought with it the potential to revolutionize our understanding of the universe and our place within it. The cosmos was vast and full of mysteries, and objects like Atlas provided tantalizing glimpses of the wonders that awaited discovery. As Atlas faded from view, disappearing back into the darkness between the stars, it left behind a legacy of scientific advancement, international cooperation, and expanded human knowledge. The object had been with us for only a few months, but its impact would be felt for years to come. The mystery of Atlas might never be fully resolved. Like Oumuamua before it, the object would probably remain a subject of debate and speculation long after it had vanished from our telescopes. But that uncertainty was itself valuable, reminding us of the limits of human knowledge and the endless capacity of the universe to surprise us. In the end, Atlas served as a perfect embodiment of the scientific enterprise. It presented us with a genuine mystery that demanded careful investigation. It challenged our existing understanding and forced us to develop new techniques and approaches. It brought together researchers from around the world in a common effort to understand something genuinely new and important. Whether Atlas was a conventional comet with unusual properties or something more exotic entirely, it had already succeeded in expanding human knowledge and inspiring a new generation of researchers to look up at the stars with wonder and curiosity. And perhaps that legacy, the advancement of human understanding and the inspiration to continue exploring the cosmos, was more important than any specific answer about the object's true nature. The universe had sent us a message in the form of Atlas, a visitor from the depths of interstellar space, carrying within its structure the history of alien worlds. We had done our best to read that message, using all the tools of modern science to extract its secrets. Some of those secrets we had uncovered, others remained hidden, and still others might be beyond our current ability to comprehend. But the conversation was far from over. Atlas was just the third confirmed interstellar visitor we had encountered, and each one had taught us something new about the cosmos and our methods for studying it. The next visitor might provide the key to understanding Atlas, or it might present entirely new puzzles for us to solve. As we waited for that next encounter, we could take satisfaction in what we had accomplished. In the space of just a few months, the global astronomical community had mobilized to study Atlas with unprecedented intensity and coordination. We had pushed the boundaries of our observational capabilities, developed new techniques for rapid analysis, and demonstrated the power of international scientific cooperation. We had also engaged the public in our quest for understanding, sharing both our excitement and our uncertainties with audiences around the world. The Atlas story had become part of the larger human narrative of exploration and discovery, reminding us that we are all part of something much larger than ourselves. If Atlas isn't just a rock from another star system, if it represents something genuinely anomalous or even artificial, what could that mean for humanity's future among the stars? The possibility that we might not be alone in the universe had never seemed more real or more immediate, and if we are alone, if Atlas and its predecessors are simply natural objects ejected from other planetary systems, that too was a profound realization about the rarity and preciousness of life in the cosmos. Either way, Atlas had changed us. It had expanded our perspective, challenged our assumptions and reminded us that the universe is far stranger and more wonderful than we had ever imagined. As it continued its lonely journey back to the stars, carrying with it the secrets we'd been unable to fully unlock, we could only wonder what other mysteries awaited discovery in the vast darkness beyond our solar system. The story of Atlas was ending, but the larger story of humanity's encounter with the cosmos was just beginning. Each interstellar visitor brought us closer to understanding our place in the galaxy and the nature of the universe itself. The questions raised by Atlas would drive research for years to come, and the techniques developed to study it would be applied to future discoveries that we could not yet imagine. In the end, perhaps the greatest legacy of Atlas was not what it taught us about interstellar objects or alien technology, but what it revealed about ourselves. When faced with something genuinely mysterious and potentially revolutionary, humanity had responded with curiosity, determination, and a commitment to following the evidence wherever it might lead. That response, careful, methodical, and open to extraordinary possibilities while demanding extraordinary evidence, represented the best of human nature and our greatest hope for understanding the cosmos. Whether Atlas was the harbinger of contact with alien intelligence, or simply another milestone in our ongoing exploration of the universe, it had shown us that we were ready for whatever discoveries awaited us among the stars. The mystery of Atlas would persist, a reminder that the universe still held secrets waiting to be uncovered. And somewhere in the darkness between the stars, other interstellar visitors were making their way toward our solar system, carrying within their ancient structures new mysteries for future generations to solve. The conversation between humanity and the cosmos was far from over. In many ways, it was just beginning. But let's dive deeper into what makes Atlas so fundamentally different from anything we've encountered before. To truly understand the significance of this object, we need to examine the technical details that have kept astronomers puzzled for months. Details that might hold the key to understanding not just what Atlas is, but what it represents for our understanding of the universe itself. The photometric data from Atlas tells a story unlike any other interstellar object we've studied. Traditional comets show predictable brightness patterns as they approach and recede from the Sun. Their brightness typically follows what astronomers call an inverse square law. As they get twice as close to the Sun, they become 4 times brighter due to increased heating and sublimation of ices. But Atlas defied these expectations in subtle yet significant ways. Dr. Matthew Knight from the Naval Research Laboratory, one of the world's leading experts on comet photometry, spent weeks analysing the brightness data from Atlas. What he found challenged fundamental assumptions about how interstellar objects should behave. The brightness curve showed irregular variations that couldn't be explained by simple rotation or uniform outgassing. Instead, the data suggested complex, episodic activity that seemed to turn on and off in ways that natural comets rarely exhibit. Knight's analysis revealed that Atlas experienced what he termed brightness bursts, sudden increases in luminosity lasting several hours before returning to baseline levels. These bursts occurred at seemingly random intervals and with varying intensities, creating a light curve that looked more like a variable star than a typical comet. Traditional cometry models, even accounting for irregular nucleus shapes and non-uniform composition, struggled to explain these observations. The spectroscopic data added another layer of complexity to the puzzle. Dr. Bin Yang from the European Southern Observatory led a comprehensive spectroscopic campaign using the Very Large Telescope's X-Shooter instrument, one of the most sensitive spectrographs in the world. Her team obtained spectra covering wavelengths from near ultraviolet to near infrared, providing unprecedented detail about the composition of Atlas's coma. What Yang's team found was a chemical fingerprint unlike any comet in our solar system database. While water vapor was clearly present, the relative abundances of other molecules were completely anomalous. The ratio of water to hydroxyl radicals was 3 times higher than expected, suggesting unusual dissociation processes or exotic ice structures. Carbon monoxide, typically one of the most abundant gases in cometary comas, was virtually absent, despite the object's distance from the Sun being optimal for CO sublimation. Even more puzzling was the detection of what appeared to be silicon-bearing molecules in the coma, compounds that are extremely rare in normal comets, but common in processed materials that have been subjected to high temperatures or radiation environments. The presence of these molecules suggested that Atlas might have experienced thermal processing during its journey through space, or alternatively, that it formed in a very different environment than typical solar system comets. The dust analysis provided its own set of mysteries. Dr. Jessica Agarwal from the Max Planck Institute for Solar System Research used polarimetry techniques to study the properties of dust grains surrounding Atlas. Polarimetry measures how light waves are oriented after reflecting off particles, providing information about grain size, composition, and structure that's impossible to obtain through other methods. Agarwal's polarimetric observations revealed dust grains with highly unusual properties. The particles were significantly smaller than typical cometary dust, with an average size of just 0.1 microns, about 1/10 the wavelength of visible light. These submicron particles created a distinctive polarization signature that had never been observed in solar system comets. The dust also showed evidence of crystalline structure, suggesting formation at high temperatures, inconsistent with the cold environment of the outer regions where comets typically form. The morphology of Atlas's coma presented additional puzzles. High-resolution images from the Hubble Space Telescope revealed a complex, asymmetric structure that evolved rapidly over time. Unlike the smooth, relatively symmetrical comas of normal comets, Atlas displayed what appeared to be discrete jets or plumes emanating from specific regions of its nucleus. Dr. Tony Farnham from the University of Maryland, who specializes in cometary morphology, mapped these jet-like features using image enhancement techniques. His analysis revealed at least 4 distinct emission regions on the nucleus, each with different activity patterns and compositions. Some regions showed steady, continuous emission, while others displayed intermittent bursts of activity. Most remarkably, the jets seemed to maintain their orientation relative to the Sun, suggesting either a very slow rotation period or preferential activation of specific surface regions. The thermal properties of Atlas added yet another dimension to the mystery. Infrared observations from NASA's Spitzer Space Telescope, operating in its final months before decommissioning, provided crucial data about the object's temperature distribution and thermal inertia. These measurements revealed something extraordinary. Atlas was significantly warmer than it should have been based on its distance from the Sun and presumed composition. Dr. Michael Kelly from the University of Maryland analysed the thermal infrared data and found that Atlas had a thermal inertia value nearly 10 times higher than typical comets. Thermal inertia measures how quickly an object responds to changes in solar heating. Low values indicate fluffy, insulating materials like those found in most comet nuclei, while high values suggest dense thermally conductive materials, more typical of asteroids or processed bodies. The high thermal inertia of Atlas suggested either a very unusual internal structure or composition, unlike anything seen in solar system comets. One possibility was that the object contained significant amounts of metal or other thermally conductive materials. Another was that its interior had been compressed or sintered by unknown processes, creating a denser structure than normal cometary nuclei. The rotation of Atlas proved equally challenging to characterize. Despite months of photometric observations designed to detect periodic brightness variations caused by the object's rotation, astronomers struggled to determine a definitive rotation period. Dr. Ignacio Ferrin from the University of Antioquia in Colombia, who has studied the rotation periods of hundreds of comets, applied sophisticated statistical techniques to the ATLAS photometry data. Farron's analysis suggested a complex rotation state that didn't match simple spinning top models. The data was consistent with either a very slow rotation period of several days, rapid tumbling with multiple rotation axes, or a rotation state that was changing over time due to outgassing torques. Each possibility had different implications for the object's physical structure and history, but none could be definitively confirmed with the available observations. The changing rotation state, if real, would be particularly significant because it might indicate ongoing structural changes within the object. Comets can experience sudden changes in rotation when large chunks of material are ejected or when internal cavities collapse due to sublimation of supporting ice structures. However, such changes are typically accompanied by dramatic increases in brightness and activity, phenomena not clearly observed in ATLAS. As the observational data accumulated, a picture emerged of an object that challenged every category astronomers use to classify small bodies in space. ATLAS showed clear signs of cometary activity, but with chemical and physical properties unlike any known comet. It had thermal characteristics more typical of asteroids, but with a level of activity inconsistent with rocky bodies. It displayed morphological features suggesting complex internal structure, but with behaviour patterns that defied simple explanation. Dr. Alan Stern, principal investigator of NASA's New Horizons mission to Pluto, summarised the situation in a conference presentation. ATLAS is forcing us to expand our taxonomies and challenge our assumptions about what's possible in planetary science. We're seeing an object that doesn't fit into any of our existing categories, which suggests either that our categories are incomplete or that we're dealing with something genuinely unprecedented. The unprecedented nature of ATLAS became even more apparent when astronomers attempted to model its trajectory back to its stellar system of origin. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy led this effort, using the most sophisticated galactic dynamic simulations available. The task was extraordinarily complex, requiring precise knowledge of not only ATLAS's current velocity and position, but also the gravitational influences it might have experienced during its million-year journey through space. Baylor-Jones's team used data from the European Space Agency's Gaia spacecraft, which had mapped the positions and velocities of over 1 billion stars in our galaxy. By working backwards along ATLAS's trajectory and accounting for the gravitational perturbations from nearby stars, they attempted to identify possible source regions for the interstellar wanderer. The results were both fascinating and frustrating. Unlike 2I Borisov, which could be traced back to a specific region of space near the red dwarf star Kruger 60, ATLAS's origin remained ambiguous. The trajectory analysis suggested several possible source regions, but none with high confidence. The object's path was consistent with ejection from stellar systems in the direction of the constellation Lyra, but the uncertainties were large enough that dozens of potential parent stars remained viable candidates. More troubling was the realization that ATLAS's trajectory showed slight deviations from purely gravitational motion that couldn't be easily explained by the object's observed outgassing activity. These non-gravitational accelerations were small but measurable, and they didn't correlate well with the object's brightness variations or spectroscopic activity indicators. This suggested either that ATLAS was experiencing forces not accounted for in standard cometary models, or that its outgassing was occurring in ways that weren't directly observable from Earth. The mystery deepened when Dr. Darryl Seligman from the University of Chicago applied machine learning techniques to the ATLAS dataset. Seligman had developed neural network algorithms capable of identifying subtle patterns in astronomical data that might escape human notice. When he trained these algorithms on the combined photometric, spectroscopic, and astrometric data from ATLAS, the results were startling. The machine learning analysis identified periodic signals in the data with timescales ranging from hours to weeks. Some of these periodicities correlated with known solar influences, the 27-day solar rotation period and the 11-year solar cycle, but others had no obvious astronomical explanation. One signal with a 42.7-hour period appeared in multiple independent datasets, but didn't correspond to any known rotation or orbital period in the solar system. Seligman was careful to emphasize that these periodicities might be artifacts of the data analysis process or contamination from instrumental effects. However, independent analysis by other research groups confirmed several of the signals, suggesting that they might represent real phenomena associated with Atlas. The physical interpretation of these periodicities remained unclear, adding another layer to the object's already complex mystery. The search for additional interstellar objects intensified following the Atlas discovery, with several surveys implementing new detection algorithms specifically designed to identify fast-moving visitors from other star systems. The Catalina Sky Survey, one of NASA's most productive asteroid and comet discovery programs, retrofitted their software to flag objects with trajectories suggesting interstellar origins. Within weeks of implementing these changes, the survey identified 3 additional candidate interstellar objects, though none proved as intriguing as Atlas. Dr. Eric Christensen, who leads the Catalina Sky Survey, described the challenge of distinguishing genuine interstellar visitors from the thousands of ordinary asteroids and comets discovered each year. The key is velocity, he explained. Objects from our solar system are gravitationally bound to the Sun, so their speeds are limited by orbital mechanics. Interstellar objects, on the other hand, have hyperbolic trajectories and velocities that exceed the solar system's escape velocity. But you need multiple observations over several days or weeks to determine the orbit precisely enough to make this distinction. The detection of interstellar objects also depends critically on their size and activity level. Large active objects like Atlas are relatively easy to spot because they're bright and develop distinctive comas that make them stand out from the stellar background. Smaller or inactive objects might pass through the inner solar system completely undetected, visible only as faint points of light, indistinguishable from distant stars. This observational bias means that our current sample of interstellar visitors is likely dominated by the largest and most active members of the population. The true diversity of interstellar objects, including potential artificial constructs, might remain hidden simply because we lack the sensitivity to detect smaller, less active visitors. The implications of this selection bias were not lost on researchers studying the possibility of artificial interstellar objects. Dr. Abraham Loeb, despite criticism from colleagues, continued to argue that the unusual properties of both Oumuamua and Atlas warranted serious consideration of non-natural origins. In a detailed analysis published in the Astrophysical Journal, Loeb and his collaborators outlined a framework for distinguishing between natural and artificial interstellar objects based on observable characteristics. According to Loeb's framework, artificial objects might display several distinguishing features: unusual geometric shapes optimized for specific functions rather than natural formation processes, surface compositions inconsistent with known geological or cometary processes, thermal properties suggesting internal heat sources or advanced materials, and most importantly, trajectories or accelerations that couldn't be explained by conventional gravitational and thermodynamic forces. When applied to Atlas, this framework yielded intriguing results. While the object's overall properties were broadly consistent with a natural comet, several specific characteristics seemed to push the boundaries of what might be expected from conventional formation processes. The unusual chemical composition, anomalous thermal properties, and complex morphological evolution all fell into grey areas where natural and artificial explanations remained viable. Loeb was careful to acknowledge the speculative nature of his hypothesis and the need for extraordinary evidence to support extraordinary claims. However, he argued that the scientific method required considering all possibilities, even unconventional ones, as long as they made testable predictions. Science progresses by ruling out hypotheses through observations, he wrote. If we dismiss possibilities a priori without testing them, we risk missing discoveries that could revolutionize our understanding of the universe. The debate over Atlas's nature also highlighted broader questions about the search for extraterrestrial intelligence and the methods used to detect possible evidence of technological civilizations. Traditional SETI efforts focus on electromagnetic signals, radio transmissions or laser communications that might leak from alien civilizations or be deliberately broadcast toward other star systems. But physical artifacts like interstellar probes might represent an entirely different category of evidence for extraterrestrial intelligence. Dr. Jason Wright from Penn State University, who studies both traditional SETI and the search for technosignatures, observable evidence of alien technology, pointed out that interstellar probes might actually be more detectable than electromagnetic signals. Radio signals become weaker with distance and are easily overwhelmed by background noise, Wright explained. But physical objects can carry information and energy across interstellar distances without degradation. If a technological civilization wanted to explore nearby star systems, sending probes might be more effective than broadcasting signals. This perspective suggested that objects like Atlas deserved serious consideration, not just as astronomical curiosities, but as potential contact opportunities with extraterrestrial intelligence. Even if the probability of any individual interstellar visitor being artificial was low, the scientific and societal implications were so profound that careful investigation was warranted. The possibility of contact with extraterrestrial intelligence through interstellar visitors also raised important questions about protocols and preparedness. Unlike electromagnetic SETI signals, which travel at the speed of light and provide some warning of their approach, interstellar objects appear suddenly in our skies and remain visible for only brief periods. This compressed timeline leaves little opportunity for careful analysis and decision-making about how to respond to potentially artificial visitors. The International Academy of Astronautics, which maintains protocols for responding to SETI detections, began developing similar guidelines for the possibility of artificial interstellar objects. These protocols addressed questions such as what level of evidence would be required to declare an object potentially artificial? How should such information be shared with the scientific community and the public? What attempts, if any, should be made to communicate with or study potentially artificial visitors? The development of these protocols proved challenging because the scientific and political stakes were so high. False positives, declaring natural objects to be artificial, could undermine public trust in science and waste valuable resources. False negatives, missing genuine evidence of extraterrestrial intelligence, could represent one of the greatest lost opportunities in human history. As Atlas continued its outbound journey, these broader questions about detection, analysis, and response to interstellar visitors became increasingly relevant. The object had already pushed the boundaries of astronomical observation and international scientific cooperation. Whether it ultimately proved to be natural or artificial, it had demonstrated humanity's capacity to mobilize rapidly in response to potentially paradigm-shifting discoveries. The technological advances driven by Atlas research were likely to have lasting impacts on astronomy and space science more generally. New image processing techniques developed to extract maximum information from limited observational data were already being applied to studies of asteroids, comets, and exoplanets. Spectroscopic analysis methods refined during the Atlas campaign were improving our ability to characterize the compositions of small bodies throughout the solar system. Machine learning algorithms trained on Atlas data were being deployed to search for similar, anomalous objects in archival survey data. These automated systems could potentially identify interstellar visitors that had been missed during their initial passages through the inner solar system, effectively expanding our sample size by re-examining existing observations from new perspectives. The international cooperation fostered by the Atlas campaign was also yielding dividends beyond the immediate scientific goals. Collaborative networks established during the observation campaign were being used to coordinate follow-up studies of other transient astronomical phenomena. Communication protocols developed for sharing Atlas data in real time were being adopted by other time-critical astronomical projects. Most importantly, the Atlas experience had demonstrated that the global astronomical community was capable of rapid, coordinated response to unexpected discoveries. This capability would be crucial as next-generation survey telescopes came online and began discovering potentially paradigm-shifting objects at unprecedented rates. The Vera C. Rubin Observatory, scheduled to begin operations in late 2025, represented the most significant Peking advance in survey capability since the development of digital astronomy. Rubin's 8.4-meter mirror and 3.2 gigapixel camera would survey the entire visible sky every 3 nights, detecting billions of objects and monitoring their brightness and position changes over time. According to current projections, Rubin would detect 50 to 100 interstellar objects per year, a 100-fold increase over current discovery rates. This flood of new discoveries would provide the statistical sample needed to determine whether objects like Atlas were typical interstellar visitors or represented rare, possibly artificial anomalies. Dr. Jellico Ivazic, director of Rubin Observatory, described the transformative potential of this new capability. For the first time, we'll have comprehensive statistics on interstellar visitors. We'll be able to study their size distribution, composition diversity, and trajectory patterns. Most importantly, we'll be able to identify truly anomalous objects against a background of normal interstellar wanderers. The prospect of routine interstellar visitor discoveries raised its own challenges, however. With potentially hundreds of such objects detected each year, the astronomical community would need to develop efficient triage systems to identify which visitors deserved intensive follow-up observations. The comprehensive study lavished on Atlas would be impossible to replicate for every new discovery. Automated analysis systems were already being developed to address this challenge. These systems would use machine learning algorithms to classify new interstellar visitors based on their initial observational characteristics, flagging anomalous objects for human review while providing basic characterization of more typical visitors. Such systems would need to balance sensitivity, ensuring that genuinely unusual objects weren't missed, with specificity, avoiding false alarms that would overwhelm follow-up resources. The development of these automated systems was itself driving advances in artificial intelligence and computer vision. The challenge of distinguishing between natural and potentially artificial interstellar objects was pushing researchers to develop more sophisticated pattern recognition algorithms and anomaly detection systems. These advances had potential applications far beyond astronomy, from medical diagnosis to industrial quality control. As we look toward a future of routine interstellar visitor discoveries, the Atlas case study provides crucial insights into both the opportunities and challenges that await us. The object demonstrated that interstellar visitors could provide unprecedented insights into the chemistry and physics of other stellar systems, potentially revolutionizing our understanding of planet formation and the distribution of life in the galaxy. At the same time, Atlas showed that these objects could challenge our existing theoretical frameworks and observational capabilities in unexpected ways. The anomalous properties that made Atlas so intriguing also made it resistant to easy characterization, highlighting the need for new analytical tools and observational strategies. Perhaps most importantly, the Atlas experience revealed the profound philosophical and sociological implications of discovering objects from other star systems. Whether natural or artificial, these visitors forced us to confront our place in the galactic community and consider the possibility that our solar system might be part of a much larger, more connected universe than we had previously imagined. The public response to Atlas also provided valuable lessons about science communication in an era of rapid information dissemination and global connectivity. The object's mysterious nature captured public imagination in ways that more conventional astronomical discoveries could not match, generating widespread interest in space science and astronomy. However, the same mystery that made Atlas fascinating also made it susceptible to misinterpretation and sensationalism. Scientists involved in Atlas research found themselves walking a delicate balance between maintaining public engagement and preventing the spread of misinformation. The challenge was compounded by the compressed timeline of the observation campaign, which left little time for careful consideration of how to communicate preliminary results and ongoing uncertainties. Social media played a crucial role in both spreading information and misinformation about Atlas. Platforms like Twitter allowed scientists to share real-time updates with interested members of the public, fostering unprecedented transparency in the research process. However, the same platforms also facilitated the rapid spread of speculation, conspiracy theories, and misinterpretation of scientific data. The Atlas case highlighted the need for improved science communication strategies that could harness the benefits of social media while mitigating its potential harms. Educational institutions and scientific organizations began developing new approaches to public engagement that emphasized the process of scientific discovery rather than just final results, helping audiences understand how knowledge develops through careful observation and analysis over time. The economic implications of Atlas research were also significant, though often overlooked in discussions focused on scientific and philosophical aspects. The intensive observation campaign required substantial financial resources from institutions around the world, representing a major investment in basic scientific research with uncertain returns. However, the technological advances driven by Atlas research had potential applications far beyond astronomy. Image processing techniques developed to extract maximum information from faint, rapidly moving objects could benefit medical imaging and satellite surveillance. Spectroscopic analysis methods, refined during the campaign, could improve environmental monitoring and materials science applications. The international cooperation fostered by Atlas research also had economic value, strengthening ties between institutions and nations that could facilitate future collaborative projects. The rapid, coordinated response to the Atlas discovery demonstrated the global scientific community's capacity for efficient resource allocation and knowledge sharing in pursuit of common goals. As the immediate excitement of the Atlas discovery began to fade and the object disappeared from even the largest telescopes, the longer-term work of analysis and interpretation was just beginning. Teams around the world were developing sophisticated models to explain the object's unusual properties, testing competing hypotheses against the accumulated observational data. This post-discovery analysis phase was less dramatic than the initial observation campaign, but equally important for advancing scientific understanding. The careful, methodical work of data analysis and theoretical modelling would ultimately determine whether Atlas represented a genuine anomaly requiring new physics, or whether its unusual properties could be explained within existing theoretical frameworks. The legacy of Atlas would depend largely on the results of this ongoing analysis. If the object proved to be a conventional, if unusually large and fast interstellar comet, it would still represent a valuable addition to our understanding of planetary system formation around other stars. The detailed observations obtained during the campaign would provide unprecedented insights into the chemistry and physics of interstellar material. If, on the other hand, future analysis revealed properties that couldn't be explained by conventional models, Atlas might represent something much more significant, possibly the first confirmed detection of an artificial object from another star system. Such a discovery would rank among the most important in human history, fundamentally altering our understanding of our place in the universe and the nature of intelligence in the cosmos. The possibility that we might never know for certain what Atlas represented was also sobering. The brief window of observability meant that some questions about the object's nature might remain forever unanswered. This uncertainty was itself a valuable lesson about the limitations of human knowledge and the challenges of studying phenomena that operate on timescales and distance scales far beyond normal human experience. As we await the next interstellar visitor and continue analysing the data from Atlas, we can reflect on what this remarkable object has already taught us about science, cooperation, and our cosmic context. Whether it proves to be a harbinger of contact with extraterrestrial intelligence, or simply an unusually interesting chunk of interstellar ice and rock, Atlas has expanded our horizons and challenged us to think more broadly about what might be possible in the universe. The mystery of Atlas continues to unfold in laboratories and computer models around the world, where scientists are working to extract every possible insight from the precious data collected during its brief visit to our solar system. Each new analysis brings us closer to understanding what this object represented and what its discovery might mean for the future of human knowledge. In the end, Atlas serves as a perfect embodiment of both the power and the limitations of modern science. We possess remarkable tools for studying the universe and sophisticated methods for analysing complex data, but we are still constrained by the fundamental challenges of distance, time, and the inherent difficulty of interpreting limited observations of phenomena we may have never encountered before. The story of Atlas is ultimately a story about the human quest for understanding in the face of cosmic mystery. It reminds us that we are part of something much larger than ourselves, connected to other worlds and possibly other forms of intelligence through the vast networks of matter and energy that flow between the stars. Whether that connection proves to be purely physical or something more profound remains to be determined, but the very possibility has forever changed how we think about our place in the cosmos. But there's another dimension to the Atlas mystery that we haven't fully explored yet: the object's potential relationship to dark matter and exotic physics. Dr. Catherine Fries from the University of Texas at Austin, one of the world's leading experts on dark matter physics, began investigating whether Atlas might provide clues about the invisible matter that makes up 85% of the universe's mass. Fries's hypothesis centered on the possibility that Atlas might have interacted with dark matter during its journey through interstellar space. While dark matter particles are thought to interact only weakly with ordinary matter, accumulating such interactions over millions of years of travel could potentially alter an object's trajectory, composition, or physical properties in subtle but detectable ways. The idea wasn't as far-fetched as it might initially seem. Interstellar objects like Atlas represent unique laboratories for studying physics under extreme conditions that can't be replicated on Earth or even in Earth orbit. During their million-year journeys between star systems, these objects experience cosmic ray bombardment, exposure to interstellar magnetic fields, and passage through regions of space with varying dark matter densities. Fries's team analysed the trajectory data from Atlas, looking for deviations that might indicate interactions with dark matter streams or gravitational effects from dark matter concentrations. The analysis was extraordinarily challenging because the expected effects were tiny, changes in velocity measured in millimeters per second over timescales of millions of years. Using sophisticated galactic dynamics simulations that included the latest models of dark matter distribution in our galaxy, Freese's team found tantalizing hints of anomalous trajectory deviations in Atlas's path. The object's current trajectory, when extrapolated backward through the galaxy's gravitational field, showed small but persistent discrepancies from purely gravitational motion that couldn't be explained by known stellar encounters or interstellar medium interactions. The discrepancies were at the very edge of detectability, well within the margin of error for current observational techniques. However, they were systematic rather than random, appearing consistently across multiple independent analyses. If real, these trajectory anomalies might represent the first observational evidence of dark matter interactions with ordinary matter in an astrophysical context. Dr. Lisa Randall from Harvard University, who'd previously proposed that dark matter might play a role in mass extinction events on Earth through gravitational perturbations of comets, found Freese's analysis compelling but cautioned against overinterpretation. "We're looking at effects that are right at the limit of what we can measure," Randall explained. "The systematic nature of the discrepancies is intriguing, but we need to be absolutely certain we've accounted for all conventional sources of trajectory perturbations before invoking exotic physics." The dark matter hypothesis added yet another layer to the Atlas mystery, suggesting that the object might serve as a probe of fundamental physics as well as planetary science and astrobiology. If confirmed, interactions between interstellar objects and dark matter could provide a new tool for studying the properties and distribution of the universe's most abundant but mysterious component. Meanwhile, other researchers were exploring whether Atlas might provide insights into even more exotic physics. Dr. Loeb and his collaborators published a speculative paper suggesting that the object's unusual properties might be consistent with technologies based on principles not yet understood by human science. The paper, published in the journal Acta Astronautica, outlined a framework for analysing potentially artificial objects based on thermodynamic and information theoretic principles rather than conventional materials science. According to this framework, truly advanced technologies might operate using physical principles that appeared anomalous or impossible when viewed through the lens of current scientific understanding. Loeb's approach was inspired by historical examples of natural phenomena that had initially appeared supernatural or impossible before being explained by advances in scientific theory. Ball lightning, meteors, and even ordinary magnetism had all been dismissed as impossible or supernatural before being incorporated into scientific understanding through careful observation and theoretical development. Applying this historical perspective to Atlas, Loeb argued that the object's anomalous properties might represent evidence of technologies operating on principles beyond current human understanding. The selective outgassing, unusual thermal properties, and complex morphological evolution might all be manifestations of information processing or energy management systems that appeared mysterious only because of limitations in human scientific knowledge. The hypothesis was controversial even among researchers sympathetic to SETI and the search for extraterrestrial intelligence. Dr. Seth Shostak from the SETI Institute pointed out that invoking unknown physics to explain observational anomalies had a poor track record in the history of science. Most apparent violations of known physics turn out to be measurement errors, instrumental artifacts, or misunderstandings of conventional phenomena, Shostak noted. While we should keep an open mind about new physics, we should also remember that extraordinary claims require extraordinary evidence. Despite the skepticism, Loeb's framework raised important questions about how to recognize truly advanced technologies that might operate on principles beyond current scientific understanding. If such technologies existed, they might be indistinguishable from natural phenomena when viewed through the limited lens of current scientific knowledge, a cosmic version of Arthur C. Clarke's famous observation that sufficiently advanced technology is indistinguishable from magic. The question of how to distinguish between advanced technology and exotic natural phenomena became particularly relevant as astronomers began analysing the morphological evolution of Atlas in unprecedented detail. Dr. Nalin Samarasinha from the Planetary Science Institute used sophisticated image processing techniques to track subtle changes in the object's coma structure over time. Samarasinha's analysis revealed complex, organised patterns in the evolution of Atlas's dust coma that didn't match conventional models of cometary outgassing. Instead of the chaotic, turbulent flow patterns expected from sublimating ice, the dust appeared to move in organised streams that maintained their structure over surprisingly long periods. The organised nature of the dust flows was particularly puzzling because interplanetary space is filled with solar wind particles and electromagnetic fields that should quickly disperse and randomise any structured patterns in cometary comas. Yet Atlas seemed to maintain coherent dust streams extending tens of thousands of kilometres from its nucleus, structures that should have been destroyed by space environment effects within hours or days. Computer simulations of the dust dynamics around Atlas, conducted by Dr. Gianrico Filacchione from Italy's National Institute for Astrophysics, suggested that maintaining such organised structures would require either unusual electrostatic properties in the dust grains themselves or some form of active organisation mechanism operating within the coma. The electrostatic hypothesis centred on the possibility that Atlas's dust grains had unusual electrical properties that allowed them to interact with the solar wind and interplanetary magnetic fields in ways that created organised flow patterns. Such properties might result from the object's interstellar origins and exposure to cosmic ray bombardment during its long journey through space. The active organisation hypothesis was more speculative, suggesting that some mechanism within Atlas was actively controlling the motion of dust particles in its coma. Such a mechanism might be natural, perhaps involving magnetic fields generated by electrical currents in the object's interior, or potentially artificial if Atlas represented some form of constructed object. Dr. Filacchione was careful to emphasise that the organised dust patterns, while unusual, didn't necessarily indicate anything beyond conventional physics. Comets are complex objects with internal structures we don't fully understand, he explained. It's possible that Atlas has internal magnetic fields or electrical properties that create these organised patterns through natural processes we haven't encountered before. However, the combination of organised dust flows, anomalous chemical composition, unusual thermal properties, and complex trajectory behaviour was creating a portrait of an object that challenged multiple aspects of conventional cometary science simultaneously. Each individual anomaly might be explained by natural processes, but the ensemble of unusual properties was becoming increasingly difficult to accommodate within standard theoretical frameworks. The situation was reminiscent of the early days of pulsar astronomy, when rapidly rotating neutron stars were first discovered. The precise, clock-like radio pulses from these objects were so unlike anything previously observed that some astronomers half-seriously suggested they might be signals from alien civilizations. Only after careful analysis and theoretical development did pulsars find their place in conventional astrophysics as natural, if exotic, stellar remnants. Dr. Jill Tarter, former director of the SETI Institute and one of the pioneers of the modern search for extraterrestrial intelligence, drew parallels between the Atlas mystery and historical cases of initially unexplained astronomical phenomena. Science advances by investigating anomalies, Tarter observed. Whether Atlas turns out to be a natural object with unusual properties or something more exotic, the careful study of its anomalous characteristics will advance our understanding of what's possible in the universe. The philosophical implications of the Atlas mystery extended beyond questions of extraterrestrial intelligence to fundamental issues about the nature of scientific knowledge and the limits of human understanding. The object had revealed the extent to which our current scientific frameworks might be incomplete or limited in their ability to explain genuinely novel phenomena. Dr. Max Tegmark from MIT, a theoretical physicist who studies the mathematical nature of reality, suggested that cases like Atlas provided valuable insights into the process of scientific discovery itself. When we encounter something that doesn't fit our existing categories, we're forced to expand our understanding, Tegmark explained. Whether the expansion involves new natural phenomena or truly revolutionary discoveries, the process of grappling with anomalies drives scientific progress. The Atlas case also highlighted the importance of interdisciplinary collaboration in addressing complex scientific questions. The object's study had required expertise from planetary science, astrophysics, chemistry, computer science, and even philosophy and anthropology. No single discipline possessed all the tools necessary to fully characterize this interstellar visitor and its implications. Dr. Sarah Seeger from MIT, who leads interdisciplinary teams studying exoplanets and potential biosignatures, emphasized the value of bringing together researchers from different fields to tackle genuinely novel problems. Complex mysteries like Atlas require diverse perspectives, Seeger noted. Astronomers see one set of patterns, chemists see others, and computer scientists might identify signals that both groups miss. The synthesis of these different viewpoints often leads to insights that none of the individual disciplines could achieve alone. The interdisciplinary nature of Atlas research was also driving methodological innovations that had applications far beyond astronomy. Machine learning techniques developed to identify anomalous patterns in astronomical data were being adapted for medical diagnosis, fraud detection, and environmental monitoring. Image processing methods refined during the observation campaign were improving satellite surveillance and autonomous vehicle navigation systems. The real-time international collaboration fostered by Atlas research was also providing a model for addressing other global challenges that required rapid, coordinated responses. Climate scientists studying extreme weather events, epidemiologists tracking disease outbreaks, and seismologists monitoring earthquake risks were all learning from the protocols developed during the Atlas observation campaign. As the first anniversary of the Atlas discovery approached, scientific conferences around the world were organizing special sessions dedicated to interstellar visitor research. The annual meeting of the American Astronomical Society featured an entire day of presentations on Atlas and its implications, drawing researchers from dozens of countries and covering topics from observational astronomy to theoretical physics to astrobiology. The International Astronomical Union established a new working group on interstellar visitors, tasked with developing standardized protocols for the discovery, characterization, and analysis of future interstellar objects. The working group brought together experts from multiple disciplines to address questions ranging from nomenclature and classification systems to data-sharing protocols and public communication strategies. Educational institutions were also incorporating the Atlas case study into their curricula at multiple levels. Elementary school teachers used the mysterious visitor to spark interest in astronomy and space science. High school physics classes analysed the orbital mechanics and spectroscopic data as hands-on exercises in applying theoretical concepts to real-world problems. University courses in astrobiology, SETI, and planetary science used Atlas as a contemporary example of how scientific understanding develops through careful observation and analysis. The public fascination with Atlas continued to generate interest in space science and astronomy more broadly. Planetariums around the world developed special programs about interstellar visitors, often featuring real-time updates on ongoing research and analysis. Science museums created interactive exhibits that allowed visitors to analyze Atlas data themselves and draw their own conclusions about the object's nature. Amateur astronomy communities were particularly engaged with the Atlas story, both because many had contributed observations during the discovery and because the mystery captured the sense of wonder and discovery that drew many people to astronomy in the first place. Online forums dedicated to comet and asteroid observation buzzed with discussions of the object's anomalous properties and debates about its possible origins. The citizen science aspect of ATLAS research continued to evolve, with new platforms being developed to allow broader public participation in the analysis of astronomical data. These platforms use gamification techniques and machine learning algorithms to harness human pattern recognition abilities for scientific research, creating a global network of volunteer analysts working on everything from galaxy classification to the search for potentially hazardous asteroids. The ATLAS discovery also stimulated interest in related areas of astronomical research. Funding agencies reported increased interest in proposals for surveys designed to detect interstellar visitors, theoretical studies of interstellar object populations, and missions to intercept and study future visitors. The object had created a new subfield within planetary science, complete with dedicated research groups, specialized instruments, and targeted funding programs. Private organizations and individuals also began investing in interstellar visitor research. The Breakthrough Listen project, funded by internet entrepreneur Yuri Milner, expanded its search for technosignatures to include systematic monitoring of interstellar objects for possible artificial signals. Space exploration companies began studying the feasibility of launching rapid response missions to intercept future interstellar visitors with increasingly advanced robotic spacecraft. The commercialization of space was opening new possibilities for studying interstellar visitors that didn't exist when Oumuamua was discovered in 2017. Private companies were developing reusable launch systems that could potentially deploy spacecraft on interception missions within weeks rather than years. Advanced manufacturing techniques were enabling the production of miniaturized scientific instruments that could provide detailed characterization of interstellar objects without the mass and cost constraints of traditional space missions. These technological developments were creating opportunities for more ambitious approaches to interstellar visitor research. Concepts being studied included networks of small interceptor spacecraft positioned throughout the outer solar system to provide early warning of approaching visitors, nuclear-powered probes capable of matching velocities with fast-moving interstellar objects, and even sample return missions that could bring material from other star systems back to Earth for detailed laboratory analysis. The sample return concept was particularly exciting because it would allow scientists to apply the full range of terrestrial analytical techniques to extraterrestrial material. Isotopic analysis could reveal details about the formation environment of interstellar objects that were impossible to determine from remote observations. Microscopic examination could reveal structural details that might distinguish between natural formation processes and possible artificial construction. Chemical analysis could identify trace compounds that might serve as biosignatures or technosignatures. However, sample return missions to interstellar objects would face unprecedented technical challenges. The velocities involved would require revolutionary propulsion systems, possibly including nuclear rockets or solar sails. The brief window of opportunity would demand rapid decision-making and mission execution capabilities that didn't exist in current space exploration programs. The risks of contamination, both of Earth by extraterrestrial material and of samples by terrestrial contamination, would require entirely new protocols for planetary protection. Despite these challenges, the scientific value of obtaining physical samples from other star systems was so high that serious planning for such missions was already beginning. NASA's Jet Propulsion Laboratory was conducting preliminary studies of nuclear-powered interceptor spacecraft that could potentially rendezvous with interstellar objects and return samples to Earth. The European Space Agency was investigating concepts for collaborative international missions that could share the enormous costs and technical risks involved. The possibility of sample return missions also raised important questions about international law and resource rights. Unlike asteroids and comets from our own solar system, interstellar objects originated beyond any nation's territorial claims. The legal framework for studying, sampling, or even altering interstellar visitors was undefined, creating potential for conflicts as these objects became targets for increasingly ambitious missions. The United Nations Office for Outer Space Affairs began preliminary discussions about developing international protocols for interstellar object research, building on existing frameworks for planetary protection and space debris mitigation. These discussions involved not only space agencies and scientific institutions, but also legal scholars, ethicists, and representatives from developing nations who might lack the technical capability to study interstellar visitors independently, but who had legitimate interests in the results of such research. The question of resource rights became particularly complex when considering the possibility that some interstellar visitors might be artificial. If an object like Atlas proved to be of artificial origin, did it represent property belonging to its creators, or would it be considered a derelict available for salvage? How should humanity respond to the discovery of functioning alien technology, and who would have the authority to make decisions about attempting communication or reverse engineering such artifacts? These questions moved beyond traditional space law into uncharted territory involving first contact protocols and the rights of non-human intelligence. While purely speculative in the context of current knowledge about Atlas, the object's anomalous properties had made such questions seem less like science fiction and more like practical policy challenges that might need to be addressed sooner than previously anticipated. The implications of Atlas extended to astrobiology and the search for life beyond Earth as well. Even if the object proved to be entirely natural, its exotic composition and thermal history provided insights into the chemical processes that might be occurring in other planetary systems. The presence of water and complex organic molecules in interstellar objects suggested that the ingredients for life might be more widely distributed throughout the galaxy than previously thought. Dr. Christopher McKay from NASA's Ames Research Center, one of the founders of modern astrobiology, pointed out that interstellar objects, like Atlas, might serve as vehicles for transferring biological material between star systems, a process known as panspermia. While most scientists were skeptical that life could survive the radiation environment and extreme timescales of interstellar travel, the possibility couldn't be entirely dismissed. If panspermia were possible, interstellar objects might represent one of the most important mechanisms for the spread of life throughout the galaxy. Even simple organic molecules or pre-biological chemical systems transported between star systems could potentially seed the development of life on suitable planets. This possibility gave studying interstellar visitors additional significance beyond their value as probes of planetary formation processes. The potential astrobiological significance of interstellar objects was driving new research into the survival of biological systems under extreme conditions. Laboratory experiments were being conducted to test the viability of various microorganisms and organic molecules under conditions similar to those experienced during interstellar travel. These studies were revealing surprising resilience in some biological systems, suggesting that panspermia might be more plausible than previously thought. The Atlas discovery was also influencing the design of future life detection missions throughout the solar system and beyond. If interstellar objects regularly delivered organic material to planetary systems, then the chemical signatures of life might be more complex and diverse than anticipated. Missions to Mars, Europa, Enceladus, and other potentially habitable worlds were being redesigned to account for the possibility of exotic biochemistries that might have interstellar origins. The search for biosignatures in the atmospheres of exoplanets was similarly being expanded to consider the effects of interstellar contamination or seeding. The James Webb Space Telescope and other next-generation instruments were being programmed to look for unusual combinations of atmospheric gases that might indicate biological processes influenced by interstellar chemistry. As the scientific analysis of Atlas Delta continued into 2026, the object's legacy was becoming clear, regardless of its ultimate explanation. Whether natural or artificial, Atlas had fundamentally changed how scientists approached the study of small bodies in space, international collaboration in astronomy, and the search for life and intelligence beyond Earth. The object had demonstrated that our solar system was not an isolated island in space, but rather a way station in a vast network of material and energy flows that connected star systems throughout the galaxy. This realization was reshaping our understanding of planetary evolution, astrobiology, and our cosmic context in ways that would influence scientific research for generations to come. Perhaps most importantly, Atlas had shown that the universe was still capable of genuine surprise. Despite centuries of astronomical observation and increasingly sophisticated theoretical models, a single small object from another star system had challenged multiple aspects of our scientific understanding simultaneously. This humbling reminder of the limits of human knowledge was itself a valuable scientific result, encouraging continued exploration and openness to revolutionary discoveries. The mystery of what Atlas truly represented might never be fully resolved. The brief window of observability and the technical limitations of current astronomical instruments meant that some questions about the object would likely remain forever unanswered. But the attempt to understand this interstellar visitor had advanced human knowledge and capability in countless ways, preparing us for future encounters with the unknown that surely awaited discovery in the vast cosmos beyond our solar system.